In this video, I would like to tell you a little bit about the history of our models of atoms and one experiment in particular by a guy named Rutherford that is really relevant to the stuff that we've been talking about in the last few lectures. Okay, so the first modern idea of atoms came from Dalton. Okay, so Dalton was a chemist, and by doing a bunch of chemistry experiments, he was able to show that if you create materials out of other materials, that it always works in certain proportions. Okay, and those proportions not only are, some fraction oxygen and some fraction hydrogen, let's say, when you create water or hydrogen peroxide or some other material, but when you make multiple different kinds of materials out of the same stuff, like say water and also hydrogen peroxide, the proportions are related to each other in very particular ways. They kind of suggest that there's a Lego-like relationship between them, that you have these little discrete units that you can put together in some different ways. Okay, but Dalton's model for atoms didn't have any internal structure. Okay, so we were imagining sort of billiard ball type atoms. Okay, and then, by filling in the periodic table, Mendeleev was able to, basically come up with a few dozen kinds of atoms, and that was thought that those were all just different types of essentially billiard balls. Okay, well, so then the next development after Dalton in the model of the atom was from Thomson. Okay, and Thomson had discovered electrons. Okay, and so to incorporate electrons into the model of an atom, he came up with what we call the plum pudding model. So the idea behind the plum pudding model is that you have some sort of positively charged stuff, and inside that you have some little negatively charged electrons. Okay, so you can think of these like raisins in a cookie or something like that. His weird British model was plum pudding, so this kind of goo with some chunks in it. Okay, and then the positively charged atom was balancing out the charge, so that the atom was overall charge neutral. Okay, so this was the model for a few years, and then next came Rutherford. Okay, and this is the experiment I really wanted to talk about this time. Okay, so the experiment that Rutherford did looked like the following. So he took an oven. I guess it doesn't really matter if it's an oven. He took a chamber, and he had some radioactive material inside it, and it sent out beams of helium atoms. Okay, so in fact they were just helium nuclei, so helium plus 2. So they're positively charged, and they're very heavy compared to, say, electrons, but these are things that you get from radioactive decays. Okay, so he then took some gold foil. Okay, and you use gold for this because you can pound gold foil extremely thin and have it still, maintain a foil. For other things, it'll, rip if you try to do that. But you can get gold to be very, very thin. Okay, so the idea here is that the helium atoms are able to go straight through that foil most of the time. Okay, and according to the Thomson model for an atom, what you would expect to have happen is maybe these nuclei go through and are deflected a little bit as they move pretty close to one of these electrons. Okay, so you expect some sort of small adjustment to what's going on based on that. And so, according to the Thomson model, what you expect to see is essentially some small distribution of where these things go. Okay, so the last bit of the experiment is that there's a screen here where you can detect when the little radioactive particles, the helium nuclei, hit that screen. Okay, so you can measure where they go. All right, so this is the Thomson prediction in green. What Rutherford actually saw was dramatically different. Okay, so he saw most of the particles went straight through, totally undeflected, but a few were deflected a large amount, like this, and a few actually bounced straight back the way they came. Okay, Thomson's model cannot explain the bouncing straight backward. Even if the helium hit electrons, say, directly, electrons are so much lighter than these particles, and they knew that even then, that the electron would be bounced away and the nucleus would go straight through. Okay, so the explanation for this, for Rutherford's observations, is that the atom is not some big cloud of positive charge that has little electrons stuck in it, but rather there's a tiny hard nucleus and that explains why some of the particles bounce straight back the way they came. If you hit the nucleus, you just bounce backwards. And the nucleus has almost all of the mass in an atom. Okay, otherwise, the atom is mostly empty space. Okay, and the electrons are somewhere in that mostly empty space. Okay, so if you're going to draw this out, then what you would expect to see here is essentially your small positively charged nucleus like this, and then you have these little electrons that are in sort of this empty space around it, and your whole atom is kind of, this thing. So most of the alpha particles, most of the helium nuclei, are able to pass straight through the empty space, totally undeflected. Some will pass so close to the nucleus that they experience a large electric force and they get deflected a lot. A few will hit directly and bounce more or less straight back the way they came. Okay, so this was the prevailing model of atoms for the next, dozen or so years before the Bohr model came along.